Test, test 1, 2. Host mic, check 1. Check 1, 2. This is the host mic. Check, check 1, 2.
Okay, cool. Yeah, yeah. They're my clients. Oh, really? Yeah, one of my clients.
You are.
By the way, yeah, so I'm.
Replacing
Let me just,
Lynn,
let me get your
No, no, no.
attention for 1
Yeah,
second.
sorry about that.
Okay.
Project
Project, yes.
from here, okay?
Okay.
Check it.
Okay. Hello, everyone. Does that work?
You keep it a little closer to your mouth.
Hello, everyone.
Like, think of how does Madonna do it. There you go.
Okay. Watch me break this.
Everyone.
I just dropped my backpack.
Give me a 10, 9,
10, 9, 8, 7, 6, 5, 4,
They're next to what
3,
you can introduce
2,
them.
1.
Yes.
So I'm volunteering with
10,
Sean,
9,
the conference host,
8,
and also
7,
Zach.
6,
We're
Okay.
doing
four,
compass transcriptions.
three,
for
Oh,
the
yes.
US.
1.
I wanted to give this to
Great
you.
voice.
I'll turn this
Perfect.
on,
I'm sure you
and
have
then
Yes.
you can wear this. And also,
Yep, yep.
You know?
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Okay.
I'm going to mute that now so you can chat.
I actually don't know right now. Last talk, right? At 2 o'clock, 2:20.
Yes, the 220 talk.
Oh, Lynn's coming. Nice.
Lynn is not coming.
Oh, she's
sadly.
not coming. Oh,
But her CTO is.
Oh, okay.
Okay, he's
Yeah.
actually better.
Okay.
No, just kidding. Maybe not talking, but like, you know,
Yeah,
to get nerdy with.
great to end it off.
Yeah.
Yeah, I'm not sure about replacement. I can go like ask around, I guess.
No, I have Swix text.
Okay,
Yeah.
gotcha.
Okay.
Oh, also for the compass thing, do you mind if I download the app on your phone because it has to stay on you? I can send you the link and stuff too.
Yes.
I'll be here as well, like the whole thing, if anything happens.
Sounds good. Compass?
Actually, if you go to Safari, there's a link, and then I'll share the link with you.
Can you airdrop it?
Yeah, I can do that. Yeah,
Check
give me
that
one
one more
moment.
time, but let me get back to the console before you say anything because I've turned it up a lot.
Okay, sounds good.
Okay, I'm so glad you're here early. We are still missing Santosh. Okay, worst case scenario. No, I can't do that.
Do what?
I was thinking you go first and then the others get right. Like, we cannot do that.
Oh, aren't you first? Like you're introducing?
Just 2 minutes.
Oh, okay.
There is someone before you.
Oh, who is that? Santosh?
Yes.
10, 9, 8, 7, 6, 5,
I'm
4,
airdropping to you,
3,
so if you have
2, 1, 0.
Airdrop on.
Do I have it on?
I think it's Bluetooth. If you click this.
Nyla, he wants you to talk.
Hello, everyone. Hello, everyone. Is that better? Super close. Testing, testing. Okay, cool.
something you can't touch. Would you be honest with me right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it? Taking over your senses. Don't you ever fear it? Technological advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Think there's something in my bag that's weighing me down. Oh, it's just the weight of the world. Now I'm calling it out. We're a little starving for some lightning love. Can we speak honestly right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it? Taking over your senses. Don't you ever fear it? Technological advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. lost it all, you fade away. I'm picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck, can't find a door that's open. I'm losing all my hope, feels like I'm left here in two. Because I'm missing you, because I'm missing you. Oh, because I'm missing you, because I'm missing you. Because I'm missing you.
In a minute. Hello, everyone. We'll begin in a minute. Okay, we are going to get started. Hello, everyone. My name is Naila Worker, and I am here in the GPU and Inference track. I hope you all are very excited, because I think this is top of mind for all of us. Either you have a lot of GPU and you're GPU rich and want to optimize it, or you are GPU poor and need to leverage every second of your GPUs. Or maybe it's not even a GPU and learn about different hardware. So let's get started and enjoy this track. Our first speaker of the day is Santosh, and he is going to be speaking about Agnostics AI platform. And first, the talk is going to be about how to accelerate training, fine-tuning in particular for Llama. So with that, I let you go.
Thank you. All right. So great. So the talk is actually going to be about how you run things extremely easy directly from Python. And the example that I'm going to show you here is, obviously I just have 5 minutes in on my end, but I'm going to try my best to showcase how you can fine-tune pretty much 20 is an arbitrary number here, but hundreds of models that you can do right from Python without needing anything like Kubernetes, Docker, or anything on your side end. So before that, you can find the talk and the actual code for what I'm going to do in this QR code. And you will find a lot more interesting examples over there to try out and run as well. Okay, so what do we do? So Covalent is an open source / open core product on its end. And what we do is we help people write Python locally and ship the code to any kind of compute backend that you need to send it to. So what that means is, hey, you have a Python function that you want to run on a GPU. In your local laptop, open up a Jupyter notebook, add a single decorator on top to say, hey, I want to run this on H100 with 36 gigs of memory for 2 days, maximum time limit, and press Shift Enter in your Jupyter notebook, and that's it. The code gets shipped to a backend in a GPU, and you get back the result on your side end. In the open source case, it sends it to your own compute. You can attach your own compute cluster, and it runs over there. In the cloud case, it runs in our GPU cluster, and you just pay for the GPU time that it runs in. So it runs for 5 minutes, you pay for 5 minutes of H100. It runs for 10 seconds, you pay for 10 seconds of H100s on your side. And you can also bring your own compute and attach to us, and we'll help you orchestrate the entire compute that you're handling and on your side, be it your own cloud or on-prem systems or whatever it is on your end. Okay, so Covalent basically has a bunch of primitives that you define in. You can submit in jobs, which are called single functions. So essentially, all you need to do is, as I said, add a single decorator on top and say what is the compute that you need to ship it to. It goes there, it runs, and you get back the Python object back, and you just pay for the function that you're running in. We also let you run inferences, and again, it's completely Pythonic. You don't Dockerize, you don't run Kubernetes cluster, you don't do anything. You just say, hey, I have an initializer function, and I need an endpoint called /generate. And you define your Python functions. You click a single cc.deploy command in your Jupyter notebook. The entire service gets shipped to us, and we scale. You get back an API endpoint that scales to 0 or scales in its request as and when your new request comes in. You can define your custom auto-scaling mechanism, like, hey, I want to auto-scale it to 10 GPUs exactly at 9 o'clock every day. Or I want to auto-scale whenever my GPU utilization hits in 80%. Or I want to auto-scale whenever the number of requests I get in is 1,000. So you can define whatever auto-scaling you want. You can define authentication and everything happens in the background for you. You don't even need to touch a single code of Kubernetes or Docker or anything on your side. And the talk I'm going to give in is a very tiny example of what we do from our side. But if you go to this link in, there's a whole host of examples that you can run in, right from real-time time series analysis to using inverter transformers for time series, which is like a state-of-the-art time series transformer on its end, running in large systems, large language models on your serving systems, and even building an entire AI model foundry out of our just pure Pythonic code on your side. So without further ado, I'll quickly run through the code example of how you do essentially fine-tune a bunch of huge set of models directly just from Python on your end. And I'll also show you how it looks like from the front-end side as well. So it's rather simple. All you do is, I have written a bunch of normal Pythonic training functions in my local package called fine-tune and evaluate on our end. And what we are going to do is, hey, I'm going to define a Python task, which essentially calls in my fine-tune function, which is going to accept a model and data and return back a fine-tune model. So this is a simple Python function, and I'm going to say, hey, I want to run it on a 24-core CPU with 1 GPU in it of type H100 with 48 gigs of memory, and going to give a max limit of 18 hours on it. And then I'm going to say, hey, once the model is done, I'm going to accept the model and then evaluate its accuracy on its end. And finally, I'm going to just sort the model among all the best models and then pick the best model in it. And I want this to run on a CPU-based machine. I don't want to waste GPU for my sorting or whatever I'm going to do on my end. And finally, I'm going to deploy the best model that I figured that has performed well on my end. And this is, again, a simple declarative react to say, hey, this is my initialization service, and I'm going to create an endpoint called /generate. And I'm going to generate the text and give back the prediction. And finally, this is where the magic happens. To tie together all of these things, what I do is I'm going to create a workflow where I'm pretty much just going to simply loop over a bunch of models to fine-tune, call the fine-tune function, evaluate the task and get the accuracy, make a list of all the models and accuracy, sort the best models, and then deploy the model from my end. And this is completely Pythonic. And once you dispatch this to our server, which is essentially calling a single line over here, what you will go back and see is a new job that creates in our application, and all of the functions that you called will run in the respective devices that you just defined. So for instance, here is one of the evaluation steps that ran in, and it has its own machine that we ran in. It ran in L40. It ran for 6 minutes, and you get back just 87 cents to evaluate your model in. And another model ran in V100 on its end, and it ran for 6 minutes again. It costed 11 cents to do it in. And in total, you finally have deployed, fine-tuned, untrained completely in Python without needing anything like Docker or Kubernetes on your end. And we have a booth over there. Do visit us, and we can have more chat over there. Thank you, guys.
Awesome. Awesome, that was great. Now for our next speaker, we have Dylan, who is going to be speaking about the work that he's been doing at Semi-Analysis. If anyone has read any of the work that he's done on the supply chain of and analytics on the supply chain of GPUs, TPUs, and different places, this is really exciting work. So Dylan.
Hello, hello. I'm going to talk about a couple different things here, but mostly running models as well as frontier models. A couple different things, right? Like, people have been talking about stagnation, and I don't think anyone here sees that. But a lot of people have been talking about stagnation of models, and a lot of that has to just do with the fact that we haven't seen a big capabilities leap in the last bit. But that comes really from models that we're using today are largely the same as the models that were trained in 2022, right? GPT-4, 4 Turbo, 4.0, those are just smaller models that are trained for longer, so similar quality, right? 3.5 Sonnet came out recently, but again, that's actually smaller than Opus, but it's somehow better because they trained it for longer, right? But we haven't seen a extremely large model come out yet, but we will soon. But one interesting thing, right, is GPT-4 is like 1.8 trillion parameters. It's crazy, crazy expensive to run, right? 200 billion parameters. Each token requires, almost 600 gigaflops. But that's almost going to be considered a last generation model, right, in a year from now. So there's a couple of things that I wanted to talk about regarding that, right, and mostly on the inference side, because I don't think anyone here is going to try and train that kind of next generation model, but definitely we need to be able to run it. And so a few things, right? So just going to break down inference in detail, right? There's two parts of inference, right? There's prefill, there's decode. Prefill is the prompt processing, right? And the interesting thing is if you have a 2K prompt, 2K context length prompt, right? 2,000 tokens you input into GPT, that's a petaflop itself, right? And then if you have 32,000 prompt that you enter, it's 20 petaflops actually. So it's an incredible amount of compute that's required to just process the prompt. While prefill is very compute intensive, right? It's actually the opposite of decode, right? Decode is actually generating each token iteratively, right? So you process the prompt, then you generate a token, you feed it back in, and you keep going iteratively, right? And decode is extremely memory bandwidth intensive, right? You have to load the whole model from the weights, all the weights into the chip, right, or chips for decode. And the big challenge here is that, hey, if you have 1.8 trillion parameters, if you're running at a reasonable batch size, you're activating all the experts, you need to load all 1.8 trillion parameters every single token generation, right? Even if you're serving multiple users at once, that means you need, a 1.8, you need terabytes a second of memory bandwidth. You want to do 30 tokens per second. I think that's like a minimum bar for most people, right? A lot of people want hundreds of tokens per second, but even if you want 30 tokens per second per user, 64 users, you need 60 terabytes a second of memory bandwidth. Even if you look at an H100, it has like 3, right? So this is a extremely challenging systems problem. Decode, while it is very bandwidth intensive, it's actually quite cheap on the compute, which is why if you look at like OpenAI pricing or Claude pricing, you see a 3 or 4 to 1 ratio between prefill versus decode pricing, right? So the input tokens cost 1/3 that of the output tokens, or 1/4 that. So today the best models, I think 4.0 and 3.5 Sonnet are, I want to say it's $15 per million tokens, and then it's $5 per million tokens for input, 15 for output. So 5 for prefill, 15 for decode. And soon we're going to have, in the open source, so what everyone here can touch is Llama 3 405B, right? And that's going to be a real capability sort of unlock for the open source market as well as builders here, right? And I think there's a couple things that people really need to be able to implement, right? Like you can't just run Llama CPP on Llama 405B, right? Like it's just not going to work. So there's a bunch of stuff that people have to work on, whether it's using closed source libraries like TensorRT-LLM that only work on NVIDIA, or like VLLM, which is an open source library that works on AMD and Intel and soon other people's chips as well. There's a lot of stuff that people need to figure out. One of those is continuous batching, right? Because you're going to get, running inference at batch size 1 is horrendously expensive. It's great to run it if you're running it on your own personal devices, but if you're running it in the cloud, right, you're renting GPUs, you're running batch size 1, you're gonna cost yourself 10x more. 10x is a low bar, right? It's actually could be 10x to 100x more than running at a high batch, right? So you have to figure out how to run high batch sizes. Batch size is how many concurrent users you're serving. And so one of those things that makes it difficult is that users' request come in at different times, right? One person might send a request now, and then another person sends in a request 5 seconds later, but the first person's request is not done. So you need to be able to do continuous batching, i.e. be able to run through the model iteratively every time, right? And bring in new users. So continuous batching is one of the things that you have to have support of, and a lot of software today, like Llama CPP, doesn't have support for that. So either you need to build it yourself or contribute to an open source project that builds this to enable low-cost inference, right, for models like Llama 405B, right? Another one of those is disaggregated prefill or disaggregated batching, right? It depends on what you call it. But if you go back to earlier, I was discussing prefill is very compute intensive, decode is very bandwidth intensive. These are two different workloads, but when you're serving a user, right, whether it's in your own app or you're using an API, what have you, right? Like these users don't care that it's two different workloads, right? It's one workload to them. I get tokens out, right? I submit something to you and I get tokens back. But for anyone running the infra themselves, they need to be keenly aware that these are two different workloads. So one thing that a lot of people have started to do, Google's publicly said they're doing it. I believe OpenAI and Anthropic are also doing it. Other firms like Together and Fireworks have hinted that they're doing this, is disaggregated prefill, right? So once your inference volumes are high enough, you don't just run inference, you don't just replicate the model across however many chips you have, right? Say it takes four chips to serve Llama 405B, right, in the future. You wouldn't just have, if you have enough users, you don't just go 4 and then 8, 16, whatever, right? You don't just replicate that across the world. You actually do this thing called disaggregated prefill. You have one set of accelerators do the prefill, which is very compute intensive, and then you hand it off to the other set of accelerators to do decode. Now today, everyone just uses the same accelerator for that, right? H100 or A100 or maybe L40 or something, but mostly H100. But there's a reason you do this, right? And that big reason is that you have a lot of noisy neighbors, right? So if you've ever worked in like CPUs or on anything in cloud computing, noisy neighbors are a huge, huge issue. And actually, it's very trivial to dramatically slow down most inference providers' services if you just send queries in a certain way, like in a sort of malicious way. You can just slow down people's service, right? Whether that's, and that'll impact the user's time to first token, right? And I think that's a huge issue, right? If time to first token is too long, people will just quit, right, using your service. If the tokens per second varies a lot, right? For a moment, you're getting 100 tokens per second, and then it drops down to like 30, then it goes back up to 100. That's going to be really annoying to the user. So there's a lot of things around, SLA and reliability and all these things that you have to guarantee. And so disaggregated prefill is one of the techniques to do that, right? And so you don't want to have someone submit, for example, hey, I have a database and I want to run an LLM query across every single row in that database. And I'm just going to submit it to you, my service provider, because you have this cool model or what have you that's fine-tuned on some data set and whatever it is, right? If I submit 10,000 rows to you at once, that's going to kill everyone else's performance, right? So this is one of the techniques that people have for making it so, that person who you definitely want to serve doesn't impact everyone else's usage. Because once you open up your service to the real world, you're not going to be able to control who's submitting what, and rate limits are the most annoying thing ever, so that's not the correct way to go about it. Another thing is context caching, right? So Google launched this recently. They're the only one offering this today, but I think this is a really big deal because when people talk about fine-tuning, right, of models, that's great. But in reality, the best models are really expensive to fine-tune or impossible to fine-tune. Right? I can't go fine-tune 3.5 Sinet, or fine-tuning Llama 405B is going to take dozens and dozens of GPUs, right? So instead of that, and closed source models generally. So Google only does closed source models mostly for the big ones, right? So Gemini 1.5 Pro, they offered this. They brought this recently, right? Which is context caching. So instead of fine-tuning your model, why not just fill out a context length of they offer I think 2 million now today, right? 2 million context length. Why not fill it out with your data there, right? And there's a couple, advantages to that. One is you can use the best models, right? In the case of fine-tuned models, you really are focused on like the Llama 7B or Mixtral or Llama, 70B. It's kind of much lower quality models than what's available in the closed source world. So one of the things you can do is you can implement what Google has called context caching. In the open source world, we'll have super long context models soon enough, but economically, right, we talked about $15 per million tokens output and 5 million per million tokens input. If you were to have, on the best closed source models today, if you were to submit a prompt of like, 1 million tokens and most of the times you're looking at a document, you get a query back, right? Your output is very small. Almost all of the cost is just sending them that document, right? So that's gonna really, really hurt you. So for people, targeting maybe like a legal AI or like some sort of other contract review AI, a lot of these enterprise use cases, prefill is gonna dominate your cost if you're using APIs. And so Google has this context caching, and open source will have it, so models you can run yourself, and others will deploy it over time. But basically, you don't recompute the KV cache, right, the context length every single time. Instead, you cache it, but the problem is to save that takes an incredible amount of memory. So you don't save it in the GPU's memory, right? You save it on the CPU's memory or storage. And so VLLM, which is an open source library for inference, is building this currently. So if you're interested in contributing to that, check that out. Or if you're interested in using it, just start the project, right? Because, well, most of the models we have in the closed source today are only 32 or 8K or 4K context length. They're coming with longer. And being able to, dramatically reduce your costs by caching the context is gonna dramatically reduce cost, right? So now I'm just gonna talk about head in the cloud stuff instead of real usable things, which is what's coming down the pipeline, right? Which is GPT-4 was 20,000 chips for 90 to 100 days, used 38 gigawatt hours, very very expensive, cool. But what are they building now, right? OpenAI, XAI, Anthropic, many others are building 100,000 chip clusters, right? And it would train GPT-4 in 3 days, right? So it's kind of irrelevant. I'll skip over this part, too relevant. But what's a modern system capable of, right? H100 is pretty fast relative to A100, and coming down the pipeline is the new NVIDIA chips. But what's coming down with these 100,000 GPU clusters, right? It's not going to be a 1.8 trillion parameter model. It's actually going to be, it could be in the tens of trillions of parameters. The training flops, right? It talked about GPT-4 it's roughly 2 E25 flops, right? Which is, a number that's not really relevant, or 2 E25 flop. But with a 100,000 GPU cluster, you can do 10 E26, 10 E27 flops. And to run that model is going to require 200 gigabytes or terabytes a second of memory bandwidth, right? But what does that like? What does that look like, right? So this is on the top right is an image of Microsoft's data centers in Arizona where they're making GPT-5, right? They have about 100,000 GPUs here. It's 150 megawatts, right? The average home does not consume, that's like tens of thousands, if not hundreds of thousands of homes of power consumption, right? It's kind of insane. Elon's talked about his next generation cluster. He's building a 100,000 GPU cluster today, but he's talked about his next generation cluster is 300,000 GPUs. It's kind of insane, but the power cost for that alone would be $500 million a year, right? So it's people are kind of insane, but it's pretty cool. But the interesting thing here is on training, when you try and train a model today, people just talk about fully connected clusters. Every GPU is connected to every other GPU at some speed, and you have to do all your operations. But that's not really possible when you go to these super large clusters, right? So the 100,000 GPU clusters, those are being built this year, and then next year they're planning to build multiple 100,000 GPU clusters. Already you can see that it exists across multiple buildings, right? And so there's a lot of complicated networking going on, right, to connect these data centers together. And one other thing that I think is just kind of interesting to, again, head in the clouds just to think about is when you connect these chips together, there's a lot of optics, right? You can convert from electrical to optical, and then over fiber optics to connect between chips, transceivers, et cetera, right? These are extremely unreliable, right? They tend to have a failure rate of around 5 years. And so what's interesting is if you're talking about a 100,000 GPU cluster, or if you're talking about a 500,000 GPU cluster, you're going to have something fail every 5 minutes, right? Which is insane, right? How do you even deal with something in your cluster failing every 5 minutes when you're training a model, right? So this is again more of a hardware-oriented thing, but the other thing that's interesting is when you get chips, they're not all the same speed. An H100 is not an H100. There's stragglers. So if you get a large distribution of chips, what we call in the industry is called the silicon lottery. In that, like, you can buy, for example, a gaming GPU and compare it to other people's gaming GPUs on the forums, and they're actually like percentages difference in performance. But when you do a massive training cluster, you end up with, training is a synchronous workload, right? You update the weights, then you pass the gradients around, right? And then you again run through a bunch of data, update the weights, or pass the gradients around, update the weights, right? So it's a synchronous workload. So if one of them is 10% slower, then everything is 10% slower. And ByteDance had a cool paper where actually they saw a 25% decrease in speed just because one random GPU they got, while it did technically work, and NVIDIA, and according to NVIDIA, it was fine. It was like 25% slower than what they wanted, right? So this is on like a 20,000 GPU cluster even, right? So it's quite interesting that these are the problems people are running into at scale, right? So they pulled that GPU out, and then you can sort of see their performance dramatically uplifted, right? During training. And then again, this is ByteDance on a 20,000 GPU cluster, so it's a big issue. And I think some of the other stuff in this presentation is not really relevant, but I think what do these next generation systems look like is a very important question to ask yourself, right? And what do I do when I deal with that, right? Like, I think a lot of the scaffolding that people are building today for LLMs are dealing with, is dealing with hallucinations and things like that. And the hope that everyone has, or at least a lot of the AGI people have, is that, when I 100x the compute, when I build a cluster that takes $500 million of electricity and I train a model with it, it's going to make something that, yearly electricity costs, and make a model with it. And then the cluster itself costs over 10 billion, by the way, right? It's going to get rid of a lot of this, the hallucinations. It's going to let us do a lot of interesting things. Yeah, so I think that's basically all for the talk. I just wanted to, mention, sort of a reasonable thing, which is how do you run Llama 405B, kind of some strategies that people need to implement that aren't necessarily implemented yet in the open source, that are implemented at the labs, but then also, like, what are they doing, right? Because they're not worried about, Llama 405B capable models anymore.
Awesome, that was a great talk. And now we have Sunny Madra from Grok.
Hey everyone, great talk, Dylan. All right, thanks everyone. Exciting here. We basically this is a brand new talk, so I apologize if we go through it and it's a bit wonky, but I think it should be fun. What we really wanted to pay homage to today is actually, just 25 years ago we crossed the 1 gigahertz speed barrier in microprocessors. What's really crazy is when we started thinking about this talk, I actually thought it happened a lot before 1999. And I just kind of remember my own arc of getting involved with computers. But really, it was 1999. I had to kind of double and triple check it. This is the exact press release when Intel broke the 1 gigahertz speed barrier. And obviously, that was interesting, for a couple of perspectives. One, it was this really big number and moment. But two, it was really after this that Intel started to change about how they think about processors would be used, and they went for, I guess, multi-cores and things like that. And it's really something that we need to think about in terms of what's going to happen with LLMs. And really, if you go back to the rate of increase, it only took about 2 decades to get 3 orders of magnitude speed improvement in microprocessors. And so if we take a step now and look at where we are with LLMs, and we think about anywhere close to the speed of innovation, and in fact, what we hear a lot of people talk about, including Jensen, is that we're beyond the sort of curve of Moore's law. So we're actually innovating even faster than that in LLMs today. Just to look at what we've been able to do at Grok just in a short amount of time, this is between April and June of this year, we were able to increase the speed of Llama 3 8B by over 50%. And so the improvements that are happening in this area are really, really quick and super exciting. And we're really kind of keen to kind of dive into what could happen here. And so let's think about like the state of the art, right? And so, there's models today that, we can process and others can process at, say, huge inputs. Say on the equivalent of, 10,000 input tokens per second, which gets you down to, say, 1/3 of a second across, processing all of those. And when you do that, you actually end up with these capabilities from a, speed perspective that far exceed human capabilities for both integrating and analyzing information. And it's happening, really, really fast. The example I like to talk about here, and I don't know if you've used this, but I highly recommend it. It's this, really cool service called globe.engineer. And what it does is you give it a task, so it says something you're going to do. I think the example I use here, help me plan a trip to New York to try, the best pizza or something like that. And what it will do is, I couldn't even capture the whole screen here, but it'll basically figure out all the different elements that have to happen. And it's doing this live online. It's connected to the internet. So everything from the flights to the taxi options, to the hotel options, and then the food options, and then itinerary and how I can do it. And it does it all in, maybe less than 5 seconds. And if you think about what's really happening there, and I like to, think about when I plan for trips myself, I end up basically opening, tens to sometimes even hundreds of tabs. And those tabs each have like a research stream happening for me. And now all of that is solved in a simple interface, really enabled by these LLMs being able to process tokens, input tokens faster, and then ultimately output tokens faster. And it's really giving us a huge edge up in how we operate as humans. And where does this all go? Like if we start thinking about human superintelligence and optimizing and accelerating models, it really takes us to like interesting paradigms here. And we'll talk about this more in a second, but like the high level way to think about it is, what if an LLM really becomes either like an operating system or like the core of how we think about compute today, and we think about it completely differently than any of the approaches that we've had before. The way we program these things, the way our expectations are on how they analyze things. And so we're really, that's interesting in terms of where this is going in terms of superintelligence and staying away from AGI, but more about changing the paradigm from where we are today. And, the thing that crosses my mind here is what happened in the Industrial Revolution. If we think about 3 industries, let's think about making food, making cars, and making clothes. All of those before the Industrial Revolution were bespoke, right? So you'd have, people that would make 1 or 2 cars a day. You'd have people work on farms that could, maybe farm for less than a city, even a small village, or someone that was making sweaters could, make them, one a day or maybe even 1 a week. And when we had the Industrial Revolution show up, we basically had this ability to make hundreds or thousands of cars a day, food, farming at a scale that could be national, clothing that could be made at national scale. And we're really, we haven't had that in technology. The arc of technology has been, and this isn't my own framework, it comes from Paul Maritz, who was a longtime Microsoft guy, and then VMware, and then Pivotal, where he and I met. He said the first era of computing was just taking paper processes and making them digital. And he goes, that's evident in the way if you think about how the operating system is structured. Files, folders, inbox, outbox, those are all paper processes that got turned into digital processes. The next era for us was basically making those things connected, right? That's the internet era. And what we've been through now maybe in the last 15 years is form factor changes, right? Either pushing things into the cloud for scale or mobile so you can do it on your phone. But finally with AI, we're starting to get to a place where we have the industrialization in the same way we saw for those, manufacturing and physical industries, we see that for technology. So, 18 or maybe 24 months ago, if you needed to have a Photoshop made of some kind of artifact that you're going to put in a presentation, you'd go to your designer, and maybe the designer would make 1 or 2 a day for you. Now you can go to Midjourney and get 1,000 made in the next minute if you want to. So we're going through that same kind of industrialization for technology. And if we just dive in deeper here into where we go as we can get into like 10,000 complex decisions per second, just by getting this down to 0.1 milliseconds, and then if we really kind of start increasing that, it does become viable to think about the core of our computing becoming an LLM. And I think this is a real challenge for a lot of people because obviously we have existing paradigms that we're really locked into, but this paradigm shift is fundamentally different in terms of how software will be built, how software will run, and how software will scale. And we don't think about it too much today because we think about the speed associated with running LLMs and their capabilities. But if we can imagine the same growth that we saw in CPUs happen in this era, we can imagine that the core of these devices change to become something, and this is again a hat tip to Karpathy, this is a diagram that he drew. You can imagine an LLM being a core at whether what happens in video and audio, we're starting to see that today, what happens in our browsers, how we interact with other LLMs, how we interact with code interpreters, and even our file systems and how we interact with those type of things. And so what is the art of possible if we start doing this? And so I'll just kind of rattle off some things here that crossed our minds as we were putting this presentation together. We really don't spend a lot of time thinking about it, but many responses today in LLMs are sort of near real time. They're at sort of reading speed. But if we go to like instantaneous responses and decision making, this becomes a lot faster. Again, this is really evident when you think about something like that globe example I showed. What you're really able to do there is take a task that would probably take you either an afternoon or evening or a number of evenings, and it's done in just a few seconds for you. And then there's personalized experiences. Today, we don't really have a lot of personalized experiences happening. We're starting to see elements of it. I think OpenAI has started to launch a number of features that allow it to understand, specifics of your world. It could be your pets' names or kids' names or spouses' names. But really, I think, where this goes to, and a lot of people push on this. I know, 2 of my friends, Bill Gurley and Brad Gerstner, they talk about this a lot on their pod, where they really view personalization as the next major frontier. And personalization and speed are going to go hand in hand if we're going to make that work kind of seamlessly for folks. I think next is kind of a universal natural language processing. And so if we think about our interface today to software, it's, we started with sort of point and click and keyboards. We've gone to touch with our, mobile devices. But really, you start to see the power of this, and I think everyone's been super excited for the release of GPT 4.0, the voice agents. I don't think we fully got there yet, but I think we've showed the art of the possible there with what they were able to do with voice. And then that kind of mixed interaction, I would say, like, we refer to it as sort of like XRX, where it's like any type of input, reasoning, and any type of output. The example I like to tell people there, if you're trying to order something, you may want to interact with an agent in voice, but you may want to see the responses in text. And so think about if you're trying to book your haircut and you want to say, well, tell me what times are available. And then, it tells you, well, there's 9 a.m. and 11 a.m. and 3:30 and 5:30. That's hard to remember if it's just coming back to you in voice. So you want to basically have these interactions that are multimodal. That kind of touches on my second point there. And I think we're going to start to see a lot more of those interface changes as well. Advanced virtual assistants, this is like complex task scheduling. I think a lot of what we'll see in the back half of just this year is, agents start to become much more complex, and a lot of focus from LLM providers as well, I think, on making complex tasks something that are solved. It's interesting today because we measure the efficacy of a LLM through generally single shot, And I think we do that because of, going back to that where we, the start of the conversation, which is the performance barrier. But naturally, if you even take any existing LLM today and multi-shot it, its scores get a lot better. And there was a couple papers that came out recently that showed if you just had multiple agents working together on a problem, they can of a less, less parameter model, they can compete with higher parameter models just by doing sort of multi-shot reasoning or working together. And so I think we'll see a lot more of that as the speed improves, and I think there's an incredible optionality there. We saw the first cut of collaborative AI agents with Apple AI, where you see something maybe running on device, interacting with something off device. I think it's a very early implementation, and I think these things will get much more sophisticated and better. An area, we've spent a lot of time within our careers like analytics and predictive analytics. I think today everything is, pretty much action-oriented and derived off a human action. So I think if we get to a place where the speed goes up, it can be a lot more predictive. What does that really mean? It's just an agent that's always running in the background because the compute cycles are next to free. We don't see that today, but I think we get there as we get, higher up the curve. Context aware as well. And today, we are generally limited to how much context we can provide, and we're having to, even with models with bigger context windows, we still have to, be conscious of, how much compute cycles we're going to use. But I think if that becomes next to free, it becomes quite powerful for us. Creative tools and customizable content. I'll focus on the second one here. This is an area where I think many of us would like to see things go. The example I always like to, one of my favorite shows was Seinfeld. And obviously, it's not on anymore. But one of the things I like to do, when I'm bored, is go into, LLM of choice and have it write a Seinfeld episode, but made up of like modern day things that are happening. And if you ever try that, it's super fun because it does an incredible job of, identifying which character in those scenarios that you give it would have, sort of the funny or odd thing happen to them. And so the idea of, taking that beyond sort of writing and taking that to multimedia forms is going to be really, really powerful going forward. Complex decision making, before our company was acquired by Grok, we were building a company called Definitive Intelligence. So we spent a lot of time in this space, not only doing sort of, say, natural language to, analysis of SQL, text to SQL, as a lot of people would call it. But, Rick, who's sitting here with us, he was working on this really cool product for us called Pioneer, which was an automated data science agent, where it's really meant to run almost endlessly on a problem. And, you sort of define a KPI. And if you think about how a business runs, a business has a bunch of KPIs, and then a business has a bunch of data that's coming in, and then usually humans are taking that data and analyzing it as KPIs and creating PowerPoints and spreadsheets and telling either senior management or the world how well they're doing. Well, there's no reason that just shouldn't happen automatically, right? And where there's an agent just constantly, looking at the new data that's coming in, asking additional questions, diving into it. And I think we had a lot of interesting things emerge. We had let Pioneer loose on a data set of human workers and their performance reviews. And one of the things that we saw was it was able to correlate really interesting things that we couldn't think about in terms of, depending on your age and depending on your performance review, it really affected your, your output, your productivity. And so it was able to kind of discover that if you're of a certain age and you got a certain type of performance review, your productivity would fall off. Maybe Rick can correct me if I'm wrong later, but it was something along those lines, it was always an interesting example for us. And then obviously a lot of, really interesting things around dynamic optimization. This an area we're familiar from before. When a bunch of us were at Ford after the acquisition of Autonomic, we really saw, for the supply chain, if you think about how, cars are produced and how they're shipped, there's, pretty sophisticated software that does this, but it's still not efficient, right? And I think, the art of the possible with sort of what we were talking about earlier could be very, very interesting for some of our old colleagues at Ford. I'll touch on a couple more things and then leave a couple minutes for questions if there's any, but Edge AI and decentralized AI, this is pretty cool. There's a really cool project called, hyperspace.ai. What they're doing is they actually have a lot of, taking, sort of like SETI at home or even Render, and where they're basically allowing people to take their unused GPU compute and make it available in the cloud, or I guess, yeah. And why that's interesting is there's certain use cases that necessarily don't require something to be real time. And so I think we'll see a lot more of that. Now, this intersects really well with us getting more throughput and getting lower latency out of existing systems. So I think we'll see a lot more of that as well, especially because the amount of power consumption that's required. If you distribute that, you could be really interesting. And a couple more here is enhanced security and privacy. This is a big area. I was talking to one of our colleagues last night, and he was subject to a really scary type of, I guess maybe phishing call, where someone had called in, sounded very formal, and had access to a lot of information. Now we've all seen there's these kind of people that run scam call centers and people that go and attack them. But these folks armed with AI are much more sophisticated because they can create stories and narratives that are much deeper than sort of the call center worker of past. And now I think in order to protect against these systems, you'll almost need to have something on your side so that you can think about it. With our colleague, he was just so confused because the narrative was so good. The only way he could really figure out that this person was a scammer, other than hanging up on them, was saying, send me some kind of formal message, and we need them to run incredibly fast. And so, and I think this is the last set of them. Here is, education is something that's really important to us, broadly at Grok. We think about this, and we think about, making tokens available cheaper and more broadly, and being able to personalize. Salah Khan has a very good TED Talk from a couple years ago where he really highlights, it's the 2 Sigma talk, and he says you can take any student at any level, the highest levels, or even someone performing lower, and if you give them a personalized tutor, they can improve their test scores 2 standard deviations. And so imagine doing that, obviously with AIs that are, can be, one, very cheap to use, and that can be personalized to their learning experience. I was speaking to someone recently who was building an AI service for homeschooling. And what was powerful about that particular service is, let's say you have a young child and they're really into unicorns or ponies, and you want to teach them about math and math, subtraction, addition, multiplication. It's a lot easier if you frame it in the context of those things. Hey, you have 3 ponies times 2 unicorns, and what do you get from it? And so I never thought about that before, but for learning and customizing that for the interest of the person is quite powerful. So we'll see more of that. And then just interoperability and compatibility, right? I think this is an area, if you've ever been in enterprise software, the majority of money spent in deploying and maintaining enterprise software is really related to interconnectivity and interoperability and compatibility. And so having really fast and cheap AI technologies will help us really reduce a huge burden that exists on the enterprise today. So that's it. Hopefully you guys enjoyed that.
Awesome. We had such a great talk from Grok. Now we have a product manager from Crusoe, and Ivjin, and he'll be speaking about accelerating mixture of experts training. Awesome.
Thank you. Okay, just pause this here. Oh, he's up, okay, great. Thank you for coming over to our session today. Lots of really interesting stuff is happening on the AI world these days, right? With all the recent model developments and the GPU developments, it is really cool to see all the use cases. However, here I want to talk now a little bit about the infrastructure and the way how we can support the newest models of the GPUs and the newest models, the machine learning models, and how we can help that everything is working smoothly and fast and productive. So my name is Evgen Vakulenko. I'm a product manager at Crusoe. My main responsibility is the infrastructure, and specifically GPU networking infrastructure, and we are always looking for a way how we can increase the performance of that network, because as we will see later in the presentation, it is really important to do that. Now, a little bit about the Crusoe. Crusoe is an AI cloud platform which has one, I think, very important mission for all of us. It's to align the future of computing with the future of climate. There is a really strong demand right now for the computing power. The GPUs are really energy hungry. There is a lot of investments being done in the data center area, and of course that puts an additional pressure on the grid and on the energy sources. What we are trying to do here at Crusoe, we are trying to utilize the stranded energy sources, wasted energy sources, and renewables to power our data centers. We want really to be able to make sure that every time when you train your model, every time when you're using GPU for inference, you're not causing any negative impact on the climate. Now, whenever we are building the cloud, right, the AI cloud, we are building it based on three important pillars. First of all, there is a high performance pillar. As the customers are buying our services and procuring, the GPU times and training their models, we have to ensure that all the infrastructure is optimized for this training. Every time when it's not optimized, every time when there is a delay or a glitch or any sort of outage or simply not that great performance, it causes the direct impact on the customer's bottom line, it causes a direct impact on the time to train, and kind of raises the cost to train the model. Now, the second one, which I think is very important for everybody around here, is the easy to use. We want really to separate ourselves from the general purpose clouds. We do know all of them. The hyperscalers are building the great infrastructure and are trying to support each and every use case the customers might have for the cloud computing. However, in our case, we really want to focus on the experience of the AI engineers. So we want to make sure that we are providing a simpler user interface that allows developers to spin up the compute resources, to deploy the models, to train them, to use them for inference, and so on. All the underlying complexity of the infrastructure is being hidden by us, and I believe that's our job to make sure that stays the case. And now, as I mentioned before, we are climate aligned, which means we as a company really aiming to power 100% of our data centers with the renewable wasted energy sources, with some form of stranded energy sources to ensure that we are being net new zero emissions from the carbon perspective. We have a big story around that. Feel free to check it on our website or come over to our booth on the show floor, and the team will be happy to talk about that. Now, where are we present right now? We have a number of the data centers located across the US. As you see, 3 of them in the continental United States, and they are generally located close to the energy sources I was mentioning before. So we have the one in Texas, we have the one in the northern central part of the country and on the east. We are also building right now one big data center in Iceland that will be powered by the geothermal energy. I mean, again, amazing way to use the constrained energy sources or the renewables to power the data center. We are trying to follow that model, hence we are placing our data center strategically. The placement of the data center in Iceland, though, will be also very important for our EMEA customers, given the latency and the general connectivity to the Europe. That is something I think might be helpful for them as well. Now, what is our platform, right? I say Crusoe Cloud, but generally, whenever we are talking about any cloud, we are talking about 3 general types of the products. First and foremost, we have the compute. We are offering the VMs with GPUs attached to them. So every time when customer wants to get access to the GPUs, they're able to get it through the VM. They can get a bunch of VM connected together and use them as a one single training cluster. We also offer CPU instances for any potential data pre-processing or any general purpose compute tasks you might have for the data preparation, for the offload, whatever you have. From the storage perspective, we are offering ephemeral and persistent disks on the node, so those are delivered from the NVMe on the local server where your VMs are being placed. We also have the persistent block storage solution available for our customers, and we are working on providing and delivering the managed file system, the network file systems for the customers. On the networking side, of course, more traditional, more typical VPC networking. That's the network, sometimes we call it front-end network, that is used to deliver the customer traffic from the internet or from the customer environment, wherever the customer might have the data sources, to deliver that towards the VM. So that's your kind of main connectivity path to the outside world. Now, we do offer a number of the additional services on that. That's not simply connectivity. We also have the firewalls. We will be offering the load balancers soon. But generally, we are trying to follow more traditional paths for the VPC networking and the requirements the customers usually have there. Now, what is more interesting and what we will be talking a little bit later today in greater details is our rail-optimized InfiniBand cluster networking. So for those of you who don't know, typically providers, the GPU providers, are separating their network. They have the front-end network, which is used for general purpose traffic, but then all the communication between the GPUs is happening on the standalone separate network that is really high performance, low latency, and high bandwidth, and the whole topology is optimized for the GPU to GPU communication. Now, last but not least, the user experience. As I mentioned before, our main customers, our main persona, the people who are using Crusoe Cloud, are the AI developers and machine learning engineers. So we want to make sure they have what they need in order, to be successful and not to think too much about infrastructure. We also offer CLI, we have APIs, we have GUI, so everything can be automated, everything can be consumed and configured in the way you like it more. We do have a lot of customers already, and it was very fun for me to see on the floor that some of them are there and some of them are talking about their solutions. Probably this is the first time in my life, whenever I'm attending a conference and standing at the booth, I don't have to compete with all the people around us. So we do see all the companies that are presenting their solutions right now as our partners. We do partner with a bunch of them already. We have the Together AI here. We have the Boson AI, and all of them are using our infrastructure for different purposes. So Together AI, for example, they're really into using Crusoe infrastructure for the ML training, for the fine-tuning their models, and sometimes for inference. The C.AI is, they're using our compute infrastructure to train the new foundational models. This is really great. I mean, if you are the customer of Together AI, for example, or Codium or whatnot, it is likely that you have been somehow exposed to the Crusoe infrastructure. Now, the distributed training has a very specific set of problems or issues, right? There is a compute part of it when the computation is being done on the GPUs, but since we're talking about a distributed training, which means there are a lot of GPUs, at certain stages, whenever there is a training step being completed, all the GPUs have to exchange the information, have to exchange the data that they calculated on their own. This is typically done through the all reduce or all get through the all reduce process and the protocols, and it contains a forward path, the backward path, but then the networking part takes, without any optimization, about 25–30% of the network of the time of the training time. Now, This is the time when your GPUs are staying idle. They're not being able to compute anything because they have to wait for all the information to be gathered together. This is kind of a bad thing for everybody, right? This is a bad thing for the customers because they still pay for that infrastructure. They still have to wait. It delays the model training, but it's also bad for us because we have the infrastructure that is not being performant enough. There are a couple of tricks we can do. First of all, the computation and communication overlap allows you to start the network exchange or the data exchange when the computation is still ongoing. But even with that, when we were working with the customers, we saw just the reduction of about 10%, so about 25% of the training time was still spent on the networking. Me, as a product manager on the infrastructure side, are constantly being asked, like, how can we reduce that? How can we use the network as much as possible and reduce that gap? So we have been looking into that, and we were trying to figure out what would be the right cluster networking topology. How can we make sure that our data fabric that is used for connecting the GPUs is being fully optimized and is able to provide the bandwidth needed and the latency needed. The standard FAT3, those of you who have been working in the data center infrastructure before, that is something that we were traditionally doing for years. That's a great way to build a scalable, maybe non-blocking fabric, right? But there are a bunch of issues with that. First of all, if we will be connecting our servers that are shown below to a single leaf, that introduces the single choke point as well as the single fault domain, right? If we are losing the leaf, we are losing all the GPUs that are connected to that leaf. Now, what else we were thinking about is, like, look, we have that switch. We have that switch. Sorry, what is it? The time? Okay, so we have that switch that can be used for the backend traffic propagation. And why don't we use that switch from the bandwidth perspective and kind of, have an additional path? Let me just use the simple two-node example to explain the topology and to explain how we are using it. So first of all, whenever we have the GPUs that want to communicate within one server, they can use their embedded NVLink and vSwitch, and that provides a good communication. They don't have to go to the outside fabric anywhere and whatnot. Now, whenever we have the data communication between the GPUs on the different nodes, if they are connected to the single leaf, that's something we call one single rail. That means that the traffic communication will be passing through the one single leaf, just one hop away, and you will get to the destination. Now, what is interesting here is when we want to talk to the different rails, right? We have to go all the way to the spine, and that introduces the additional hop. Besides the bandwidth saturation problems, it may lead to the additional latency, which will be really important for your all reduce operations. But luckily for us, NVIDIA, with the recent version of Nickel, introduced the feature called PXN, which allows you to use the internal NV switch inside the host to communicate across the rails. So whenever we want to have the GPU 0 to communicate with the GPU 8 on the another host, we can use an internal switch to do the traffic hop between the GPUs and then send it to the leaf where it is connected to. So it still allows us to use one single hop and have access across the different rails of the GPUs. Now, we did some Nickel test results, and we saw quite a significant improvement, 50% for the small messages and 50% of the large messages. Now, those numbers here are, of course, for the smaller messages are about latency. For larger ones, we care more about bandwidth because latency tends to stay roughly the same. Those numbers are great, right? Everybody would love them, but not the customers, and it does make sense because those numbers are synthetic and more are showing you the workload that is applied to your network. What customers care about is the time to train the particular model. So we use the sparse mixture of as an example, and I mean, I'm not going to dive into the details how it works, but essentially the sparse network, the sparse mixture of experts gives you a different layers of the experts and routes the traffic between them. Whenever you're deploying that on the really large GPU cluster, that creates a ton of traffic. Like all the GPUs have to send the traffic to each other, they have to extend the information. The workload on the network is pretty significant. So we use the Mixtral model, the open source sparse mixture of experts, which is contained of 8 feed-forward blocks, 7 billions of parameters, and we use the fine-tuning to use this model to fine-tune it on 240 H100 GPUs. And we saw a quite significant improvement when we had the PXN enabled and without it. The 14% of improvement is something that can be directly connected to the time to train the model, that can be directly connected to cost of training the model, and that is something that everybody really got excited. I definitely got excited, and our customers as well, because that shows them some real value numbers they can get with a model. Now that was it from my side. Sorry for going through that. It's so fast. It's a very large topic. It's hard to talk about that, but I'm happy to answer all the additional questions, anything you guys might have. Thank you. Feel free to come over to our booth if you want to talk. I'm happy to chat more.
Awesome. With that, this track has concluded for now, so feel free to go for lunch. Awesome. Have a good day.
Because I'm missing you. I was chasing all the wrong signs, trying to hold on to something that I couldn't find. Wish you didn't captivate my mind. Now I know even the sunset's in paradise, but now something went wrong. You're moving on. I found myself on the blind side. Now you won't call. We lost it all. You fade away. I'm picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck. Can't find a door that's open. I'm losing all my hope. Feels like I'm left here in two. Because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. Picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck. Can't find a door that's open. I'm losing all my hope. Feels like I'm left here in two. Because I'm missing you. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll dive in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll dive in and I'm ready to whoa. We are a summer storm, a feeling you can't ignore. Do you ever stop to feel it caught in the afterglow? follow me to better places if I find myself at your door. Got the keys, let's go. I wanna taste this. If you showed up at my door, I would follow you to better places. If you showed up ready, let's go. Ready, let's go. Oh, oh, oh. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll dive in and I'm ready to whoa. Holding my breath and I'm ready to find strength to divide us. Gave it all we got, and I know we did the best we could. If I could go back, undo the mess, I would memorize your face before I go. But this is how we grow. Gotta give it up, sometimes there's gold. And knowing when to kill your pride. There's no one to that we know, doors that open for us in a moment. Keeping the light on, righting our old wrongs, keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over the rest, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all hopes. We can feel it, chasing the light is all we know. See in the forest, for the trees I'm keeping watch. All that is storming, waking up and turning on, keeping the light on, righting all the wrongs, keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over the rest, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all hopes. We can feel it, chasing the light is all we know. Chasing the light is all we know. Can't stop and I won't let it go. Chasing the light is all we know. Can't stop and I won't let it go. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the that you're starving for something you can't touch. Would you be honest with me right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it? Taking over your senses. Don't you ever fear it? Technologic advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Think there's something in my bag that's weighing me down. Oh, it's just the weight of the world. Now I'm calling it out. We're a little starving for some lightning love. Can we speak honestly right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it? Taking over your senses. Don't you ever fear it? Technologic advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading out broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading out broken dreams. I wanna be next to you. Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading out broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading out broken dreams. I wanna be next to you. to myself, but don't have a clue. I'm looking for some luck, can't find a door that's open. I'm losing all my hope, feels like I'm left here in two. Because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. Because I'm missing you. I was chasing all the wrong signs, trying to hold on to something that I couldn't find. Wish you didn't captivate my mind. Now I know even the sunset's in paradise, but now something went wrong. You're moving on. I found myself on the blind side. Now you won't call. We lost it all. You fade away. I'm picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck, can't find a door that's open. I'm losing all my hope, feels like I'm left here in two. Because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. Picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck, can't find a door that's open. I'm losing all my hope, feels like I'm left here in two. Because I'm missing you. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll tap in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll tap in and I'm ready to whoa. We are a summer storm, a feeling you can't ignore. Do you ever stop taking one more breath beside you, so I could find strength to divide us. Gave it all we got, and I know we did the best we could. If I could go back, undo the mess, I would memorize your face before I go. But this is how we grow. Gotta give it up, sometimes it's gold. And knowing when to kill your pride. There's no one to blame, nothing really stays the same. This is how we grow. Sometimes we hold on to let go. Sometimes we hold on to let go. Sometimes we hold on to let go. There is nothing lost between us. And oh, I know you have your reasons. Some days I'm a mess, but I know there's a rainbow over all of the past. Your head on my shoulder, but I know we're better on our own. But this is how we grow. Gotta give it up, sometimes it's gold. And knowing when to kill your pride. There's no one to blame, nothing really stays the same. This is how we grow. Sometimes we hold on to let go. Sometimes we hold on to let go. Sometimes we hold on to let go. Sometimes we hold on to. This is how we grow. Gotta give it up, sometimes it's gold. And knowing when to kill your pride. There's no one to blame, nothing really stays the same. This is how we grow. This is how we grow. Sometimes we hold on to let go. trees, I'm keeping watch. All of the storming, waking up and turning on, keeping the light on, righting all the wrongs, keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over us, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. Chasing the light is all we know. Can't stop and I won't let it go. Chasing the light is all we know. Can't stop and I won't let it go. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know.
Test 1 2. Testing 1 2 1 2 3 4. Check 1 2 1 2 3 4. Check 1 2.
Oh, I'm Gemma, by the way. Yeah,
Kathleen.
nice to meet you. Yeah, nice to meet you.
I assume you're speaking next.
Yeah.
Great. Oh, I look forward to it.
So I'm Robert. I suppose you're he's like our founder PM. He was like PM of AI Studio.
Oh, I know. Okay, sounds good. Yeah. Oh, okay, sure.
Still doing, I haven't gotten your sound right there.
No problem. Of course. I love it. Oh, sorry, I'm gonna. Hi, everyone. Please ignore me as I do some sound testing. I'm just gonna keep rambling until I get the cue that the sound is all good to go. Oh, I'm hoping that's it. Thanks, everyone.
We got an insomniac with eyes wide shut, and we got everything we need and then a little too much. I know that you're starving for something you can't touch. Would you be honest with me right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it taking over your senses? Don't you ever fear it? Technologic advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Think there's something in my bag that's weighing me down. Oh, it's just the weight of the world. Now I'm calling it out. We're a little starving for some lightning love. Can we speak honestly right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it taking over your senses? Don't you ever fear it? Technologic advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestone. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading out broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading out broken dreams. I wanna be next to you. Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestone. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow.
So much. Oh,
Don't let me
well,
go,
thank you.
I need you right now.
Thank you for letting me crash.
You wanna be next to me.
We'll take a small detour towards open models. But hi everyone, my name is Kathleen Camillion. I'm a research engineer at Google DeepMind, and as was just mentioned, I'm the technical lead of the Gemma. Before I get started, I just wanted to say how awesome it is to be here with you all today. When we were building Gemma, our North Star, the thing we were most excited about was building something to empower and accelerate the amazing work being done by the open source community. And since we launched our first models in February, I have been absolutely blown away by the incredible projects and research and innovations that have already been built on top of Gemma. So I'm particularly excited to be here with so many developers today, and especially delighted to unveil the latest advancements and additions to the Gemma model family. So without further ado, we'll get started. As many of you probably know, Google has been a pioneer in publications of AI and ML research for the past decade, including publishing some of the key research that has sparked recent innovations we've seen in AI. Research like the Transformer, Sentient Piece, BERT, to name a few. Google DeepMind has really continued this tradition and is actively working to share our research for the world to validate and examine and build upon. But Google's support of the open community for AI and ML is not just limited to publishing research. We've also been doing work to support ML across the entire technical stack for a long time, from hardware breakthroughs of TPUs, which I imagine is especially relevant for this crowd and this track, all the way to an evolution in ML frameworks from TensorFlow to JAX. Throughout all of this, open development has been especially critical for Google. Our ability to collaborate with the open source community has helped us all discover more, innovate faster, and really push the limits of what AI is capable of. So this long history of support of the open source community leads us to today and to Google's latest investment in open models, Gemma. Gemma is Google DeepMind's family of open source, lightweight, state-of-the-art models, which we build from the same research and technology used to create the Gemini models. I'm so sorry, I think that's my phone going off during this talk. Please feel free to rummage through that bag. Sorry, folks. Thank you. Wow, lesson learned that even the speaker needs to remember to silence her cell phone. All right, back to Gemma. There are a couple of key advantages of the Gemma models that I want to highlight today. The first is that Gemma models were built to be responsible by design. I can tell you from personal experience that from day 0 of developing a Gemma model, safety is a top priority. That means we are manually inspecting data sets to make sure that we are not only training on the highest quality data, but also the safest data we can. This means that we are evaluating our models for safety, starting with our earliest experimentation and ablations, so that we are selecting training methodologies that we know will result in a safer model. And at the end of our development, our final models are evaluated against the same rigorous state-of-the-art safety evaluations that we evaluate Gemini models against. And we really do this to make sure that no matter where or how you deploy a Gemma model, you can count on the fact that you will have a trustworthy and responsible AI application. No matter how you've customized Gemma models, you can trust that it will be a responsible model. Gemma models also achieve unparalleled breakthrough performance for models of their scale, including outperforming significantly larger models. But we'll get to more on that very shortly. We also designed the Gemma models to be highly extensible so that you can use a Gemma model wherever and however you want. This means they're optimized for TPUs and GPUs, as well as for use on your local device. They're supported across many frameworks: TensorFlow, JAX, Keras, PyTorch, Ollama, Transformers, you name it, Gemma is probably there. And finally, the real power of the Gemma models comes from their open access and open license. That's what's powerful about Gemma. We put state-of-the-art technology into your hands, so you can decide what the next wave of innovation looks like. When we decided to launch the Gemma models, we wanted to make sure that we could meet developers exactly where they are, which is why Gemma models are available anywhere and everywhere you can find an open model. I will not list all of the frameworks on this slide, but this is only a fraction of the places where you can find Gemma models today. This means you can use Gemma how you need it, when you need it, with the tools that you prefer for development. Since our initial launch back in February, we've added a couple of different variants to the Gemma model family. We, of course, have our initial models, Gemma 1.0, which are our foundational LLMs. We also released shortly after that CodeGemma, which are the Gemma 1.0 models fine-tuned for improved performance on code generation and code evaluation. And one variant that I am particularly excited about is Recurrent Gemma, which is a novel architecture, a state space model that's designed for faster and more efficient inference, especially at long contexts. We've also updated all of these models since their initial release. We now have Gemma 1.1, which is better at instruction following and chat. We've updated CodeGemma to have even more improved code performance. And we now have Recurrent Gemma at not only the original 2B size, but also at a 9 billion parameter size. So there's a lot going on in the Gemma model family. And I'm especially excited to tell you about our two most recent launches. The first one is actually our most highly requested feature since day 0 of launch, and that was multimodality. So we launched PaliGemma. PaliGemma, oh, thank you, I appreciate it. This is why I love the open source community, truly the most passionate developers that there are. PaliGemma is a combination of the SIGLIP vision encoder combined with the Gemma 1.0 text decoder. This combination allows us to do a variety of image text sort of tasks and capabilities, including question answering, image and video captioning, object detection, and object segmentation. The model comes in a couple of different variants. It's currently only available at the 2B size, but we have pre-trained weights that are available that can be fine-tuned for specific tasks. We have a couple of different fine-tuned variants as well that are already targeted towards things like object detection and object segmentation. And then we also have transfer checkpoints that are models that are specialized to target a couple of academic benchmarks. Up until this morning, that was our latest release, but I'm very excited to be here today with you guys because it is Gemma V2 launch day. Woo! Wow, thanks. We have been working very hard on these models since Gemma 1.0 launch date. We tried to do as much as we could to gather feedback from the community to learn where the 1.0 and 1.1 models fell short and what we could do to make them better. And so we created Gemma 2. Gemma 2 comes in both a 9 billion parameter size and a 27 billion parameter size. Both models are, without a doubt, the most performant of their size. And both models also outperform models that are even 2 to 3 times larger than these base models. But Gemma 2 isn't just powerful. It's designed to easily integrate into the workflows that you already have existing. So Gemma 2 uses all of the same tools, all of the same frameworks as Gemma 1, which means if you've already started developing with Gemma 1, you can, with only a couple of lines of code, automatically switch to using the Gemma 2 models and have increased performance and more power behind your applications. We also have the same broad framework compatibility. Again, TensorFlow, JAX, Transformers, OLLAMA, all of the ones I previously named, we have them for Gemma 2 as well. We also have significantly improved documentation. We have more guides, more tutorials, so that we can coach you through how to get started not only with inference, but with advanced and efficient fine-tuning from day 0. And finally, we really wanted to target fine-tuning as one of the key capabilities of these models. We did extensive research into how our core modeling decisions impact users' ability to do downstream fine-tuning. So we believe these models are going to be incredibly easy to fine-tune, so you can customize them to whatever your use case may be. In addition, to make it especially easy to get started using Gemma 2 models, we have made the 27B model available in Google AI Studios. This means you can go to the AI Studio homepage and select Gemma 2 now, if you wanted to, and start playing around with prompts right away. You shouldn't have to do anything except come up with an idea for how you want to push the limits of our model. I'm especially excited to see what you all end up doing with AI Studios and Gemma. And we have a couple of different ways for you to let us know what you're building, which I'll get to down the road. But if you have ideas, I'll be here all day and want to hear what you're doing with the Gemma models. But let's dive a little bit more into performance. We are incredibly proud of the models that we've made. As I mentioned, they are, without a doubt, the best, most performant models of their size, and are also competitive with models 2 to 3 times larger. So our 27B model has performance in the same ballpark as Llama 3 70B, and outperforms Grok models on many benchmarks by a fairly significant margin in some cases. But I think academic benchmarks are only part of the way that we evaluate Gemma models. Sometimes these benchmarks are not always indicative of how a model will perform once it's in your hands. So we've done extensive human evaluations as well, where we find that the Gemma models are consistently heavily preferred to other open models, including larger open models. And I'm also proud to say that the Gemma 27B model is currently the #1 open model of its size, And it currently outranks Llama 3 70B, Nemotron 340B, Grok, Claude 3, many, many other models as well. Thank you. Wow, you guys are very supportive. I appreciate it. The only other open model of any size that outperforms the Gemma 27B model is the E large model on LMSS. So we expect that you should have some fun playing around with it, especially for chat applications. We found in our evaluations that the Gemma 2 models are even better at instruction following. They're even more creative, they're better at factuality, better all around than the Gemma 1.0 and 1.1 models. The other important thing that I want to make sure to highlight from our most recent launch is the Gemma Cookbook. The Gemma Cookbook is available on GitHub now and contains 20 different recipes ranging from easy to very advanced applications of how to use the Gemma models. And the thing that I am most excited about is the Gemma Cookbook is currently accepting pull requests. So this is a great opportunity to share with us what you're building with the Gemma models, and so we can help share it with the rest of the world. And of course, I have to say, we also wouldn't mind if you started the repository. Go take a look and tell us what you're building with Gemma. So there are a couple of different ways you can get started with the Gemma 2 models. Of course, I just mentioned the cookbook. You can also apply to get GCP credits to accelerate your research using Gemma 2. We have a lot of funding available to support research. I would really encourage you to fill out an application regardless of how small or big your project is. We also, as I mentioned, have significantly improved documentation. We have many guides, tutorials, collabs across every framework so you can get started doing inference, fine-tuning, and evaluation with the Gemma 2 models. You can download them anywhere open models are available, and please chat with us on Discord or other social media channels so we can learn more about what you're building. And that's about all from me today. I am so excited to see what you all build with Gemma. I have been working on this project for almost 2 years now, and started working on this project because I, as a researcher in academia, was disappointed to see how far behind open foundational LLMs were compared to the rapid improvements we were seeing in proprietary models. So this is something that's very near and dear to my heart and that I wish I had had when I was actively part of the open source community. So I'm very excited to see the projects and the research that you all do with these models. Please engage with us on social media, on GitHub, on Hugging Face, here at the event, and let us know what you think of the models. Let us know what you think we can do better for next time. And thank you all very much. Really appreciate your time.
Awesome. So we have maybe 2 more minutes. Would you like to say what is an exciting thing that you'd like to see built with Gemma models?
Yes, I love this question. I think, as I mentioned at the beginning of the talk, I think safety and responsibility is a really crucial part of building the Gemma models, but I also think it's an area where in general, we have not seen nearly enough research. And I think that there's a lot of interesting work going on in the open source community right now about how to build more private, more secure models that will be particularly interesting. I'm really excited by some of the novel architectures that we're seeing. People adapting Gemma models to do things like the state space model, like recurrent Gemma. Probably the thing I'm most excited about is the research areas that I know nothing about. Like, I'm really excited to see people blow our minds with research ideas that never would have occurred to us. That's really what I'm looking forward to most.
And just one more question. So the V1 was out for a while. What is something that you saw that blew your mind in the past couple of months?
One of my favorite uses of the Gemma V1 models is the Gemma models use the same tokenizer as the Gemini models. So while Gemma is trained on primarily English data, the Gemini models are multimodal, they're multilingual. So this means the Gemma models are super easily adaptable to different languages. So one of my favorite projects we saw, it was also highlighted in I/O, was a team of researchers in India fine-tuned Gemma to achieve state-of-the-art performance on over 200 variants of Indic languages, which had never been achieved before, to have a model, such a small model, cover so many languages at such high quality. So that was pretty crazy to see. That was one of my favorite ones. We also had, this should be in the cookbook fairly soon, but we have a cookbook recipe that was inspired by a use case where a small business was getting sort of emails with what their new orders should be, and the emails were very all over the place. They had no structure, no format, but all sorts of different lists of requirements of what the small business needed to make for this order. And there was a small business that fine-tuned a Gemma model to take in this list of emails and output in a priority order what orders needed to be taken care of and when. So I was excited to see that like very practical application of a Gemma model as well.
Awesome. Okay. Without further ado, we should move on to the next speaker. From Fireworks AI, here we have Dima, the CTO. The CEO couldn't make it today, but Dima will give us an excellent talk.
Didn't make it today because of some personal emergency, so you got me. And as you saw, we don't have yet AI to figure out video projection, but we have AI for a lot of other things. So today I'm going to talk about Fireworks AI, and generally I'm going to continue this theme which Kathleen started about open models and how we basically focus on productionization and customization of open source models in Inference at Fireworks. But first, as an introduction, what's our background? So the founding team of Fireworks comes from PyTorch leads at Meta and some veterans from Google AI. So we combined have like probably a decade of experience in productionizing AI in some of the biggest companies in the world. And I myself personally has been core maintainer of PyTorch for the past 5 years. So topic of open source is really close to my heart. And since we kind of led this revolution of open source tool chain for deep learning through our work on PyTorch and some of the Google technologies, we really believe that open source models are the future also for Gen AI application, and our focus at Fireworks is precisely on that. So, I mean, how many people in the audience actually like use GPT and deploy it in production? And how many folks use open models or deploy the production? Oh, okay. So I was about to convince you that share of open source models is gonna grow over time, but it looks like in this audience it's already sizable. But nevertheless, so why basically this trade-off? Why go big or why go small? Currently, still like bulk of production inference is still based on proprietary models. And the catch is that those are really good models, and they're often frontier in many domains. However, the catch is that it's one model which is good on many things, and it's often served in the same way regardless of the use case. Which means that maybe if you have batch inference on some narrow domain, or you have some super real-time use case where you need to do like voice assistant or something, those are often served from the same infrastructure without customization. In terms of model capabilities, it also means like GPT-4 is great or Claude is great and can handle a lot of things, but you're often paying a lot for additional capabilities which are not needed in particular use case. You don't really need customer support chatbot to know about 150 Pokemons or be able to write you poetry, but you really want it to be really good in a particular narrow domain. So this kind of discrepancy for large models leads to several issues. One, as I mentioned, is high latency, because using a big model means longer response times, which is particularly important for real-time use cases like voice assistants. It gets more and more important with agentic stuff, because for stuff like, for example, next talk is going to be a Devin, right? Like you need to do a lot of steps for like something like agent-like application to do reasoning and call the model many times, so latency is really, really important. And often you see that you can pick smaller models like Llama or Gemma V2, which you just talked about, and achieve for a narrow domain, same or better quality while being up to 10 times faster. For example, for some of the function calling use cases, like externally benchmark from Berkeley, you get similar performance from fine-tuned Llama 3 at 10x the speed. Cost is also an issue. If you're running a big model on a lot of traffic, even if you have perhaps 5K tokens prompt and 10,000 users, and each of them calls LLM 20 times per day, on GPT-4, even on GPT-4o, it probably adds up to like 10K per day or something like several million per month. Also several million per year, which is a sizable cost of a startup. You can easily cut that with much smaller models, and that often we see as a kind of motivation for reaching out for smaller and more customizable models. But really, where open models shine is domain adaptability, and that comes in two aspects. First, there is so many different fine-tunes and customizations. I think Caitlin was mentioning about Gemma built Indian languages adaptations. Like there are models specialized for coder for medicine. If you head to Hugging Face, there are like tens of thousands of different model variants. And because the weights are open, you can always customize to your particular use case and tune quality specifically for what you need. So open source models are great. So what are the challenges? The challenges really come from three areas. First, like what we usually see when people try to use open model, something like Gemma or whatever, or Llama 8b, you run into complicated setup and maintenance, right? You need to go and find GPUs somewhere. You need to figure out which frameworks to run on those. You need to like download the models, maybe do some performance optimization and tuning, and you kind of have to repeat this process end to end every time the model gets updated or new version is released, etc. On optimization itself, there is, especially for LLMs, but generally for GenAI models, there are many attributes and settings which are really dependent on your use case and requirements. Somebody needs low latency, somebody needs high throughput, prompts can be short, prompts can be long, etc. And choosing the optimal settings across the stack is actually not trivial. And as I show you later, in many cases, you can get multiple X improvements from doing this efficiently. And finally, like just getting it production ready is actually hard. As you kind of go from experimentation to production, even just babysitting GPUs on public clouds is not as easy because GPUs are finicky, not always reliable. But getting to enterprise scale requires all the scalability technology, telemetry, observability, etc. So those are things which we focus on solving at Fireworks. So starting with efficiency, we built our own custom serving stack, which we believe is one of the fastest, if not the fastest. We did it from the ground up, meaning from writing our own CUDA kernels all the way to customizing how the stuff gets deployed and orchestrated on the service level. And that brings multiple optimizations. But most importantly, we really focus on customizing the service stack to your needs, which basically means for your custom workload and for your custom cost and latency requirements, we can tune it for those settings. What does it mean in practice? And what does customization mean in practice? For example, many use cases use reg and use very long prompts. So there are many settings you can tune actually on the runtime level and the deployment level to optimize for long prompts, which often can be repeatable. So caching is useful, or just tuning settings so the throughput is higher while maintaining latency. So this is independently benchmarkable. If you go to artificial analysis and select clone prompt, where Fireworks actually is the fastest, even faster than some of the other providers which are over there at Expo booth. We don't only focus on LLM inference. We'll focus on many modalities. As an example, for image generation, we are the fastest provider serving SDXL. We're also the only provider serving SD3. Stability's new model, because their API actually routes to our servers. And finally, as I mentioned, for like LLMs, like customization, especially for LLMs, customization matters a lot. One paradigm how to think about performance of LLMs, often it's useful for use cases, is to think about minimizing cost under a particular latency constraint. We often have customers come and say like, hey, I need to have this my interactive application. I need to generate that many tokens under 2 seconds. And that's really where like cross-stack optimizations shine, whereby tuning to a particular latency cutoff and changing many settings, you can deliver much higher throughput, multiple times higher throughput, which higher throughut basically means fewer GPUs and lower cost. In terms of model support, we support best quality open source models. We heard about Gemma now, obviously llamas, some of the ASR and text-to-speech models, pretty much from many providers. We also work with model developers. For example, Large in US is also served on Fireworks, launched last week. And as a kind of platform capabilities, as I mentioned, we have a lot of open source models to get you started, or customized ones. We do some of the fine-tuning of those models in-house. So I'm going to talk a little bit about function calling specialized models later on, or we do some of the vision language model fusion ourselves, which we release as well. And of course, the key for open source open model development is they can tune for a particular use case. So we do provide a platform for fine-tuning, whether you're bringing your data set collected elsewhere or collecting it live with the feedback when served on our platform. Specifically on customization is like one interesting feature which a lot of people starting to experiment with models find interesting is if you try to fine-tune and deploy the resulting model, how to serve it efficiently. Turns out if you do LoRa fine-tuning, which a lot of folks do, you can do smart tricks and deploy multiple LoRa models on the same GPU, actually thousands of them, which means that we can give you still serverless inference with paying per token, even if you have like thousands of model variants sitting and deployed there without having to pay any fixed cost. Of course, single model is all great, but what we see increasingly more and more in applications is model is not the product, right, by itself. You need a kind of bigger system in order to solve target application. And the reason for that is because models by themselves tend to hallucinate, so you need some grounding, and that's where like RAG or access to external knowledge bases comes in. Also, we don't have yet an industry magical multimodal AI across all the modalities, so often you have to kind of chain multiple types of models. And of course, you have all these like external tools and external actions which kind of end-to-end applications might want to do in agentic form. So I think the term which I really like, which is like popularized by Databricks, is like compound AI system, but basically increasingly seen like transition from just the model being the product to kind of this combination of maybe like RAG and function calling and external tools, etc., built together as the product. And that's pretty much the direction which we kind of see this field moving along over time. So what does it mean from kind of our perspective, what we do in this case? So we see kind of as a function calling like agent at the core of this emerging architecture, which might be connected to either domain specialized models served on our platform directly, or maybe tuned for different needs, and connected to external tools. Maybe it's a content interpreter, or maybe it's like external APIs somewhere, with really like this kind of central agentic view, kind of central model kind of coordinating and trying to triage the user requirements if it's, for example, a chatbot or something. You probably all heard about like function calling, popularized by OpenAI initially. That's basically the same idea. So yeah, the function calling is really like how to connect LLM to external tools and external elements. What does it mean in practice? So we actually focus on fine-tuning models specifically for function calling. So we released a series of models like that. Like the latest one for function V2 was released 2 weeks ago. And what you can do with that is, okay, if I manage to click on this button. What it means is like you can build applications which kind of combine free-form general chat capabilities with function calling. So in this case, this Fire function has some chat capabilities. So you could see you can like ask it what can you do, and it has like some self-reflection to tell you what it can do. It's also connected in this demo app to a bunch of external tools. So it can query like stock quotes. It can plot some charts, all those like external APIs. It can also generate images. But what it really needs to figure out is how to translate user query into, do complex reasoning, translate it into function calls. So for example, if we ask it to generate a bar chart with top 3, like with stocks of top cloud providers, like the big 3, it actually needs to do several steps, right? It needs to understand that like top 3 cloud providers means AWS, GCP, and Azure, right? And Azure is owned by Microsoft. It needs to then go do function calls, querying their stock prices, and finally it needs to combine those information and send it to chat plotting API, which is what just happened in the background. Another important aspect which you have to do for like efficient kind of function calling chat capabilities, you need to have contextual awareness. So if I ask it to add particular, if I ask it to add Oracle to this graph, it needs to understand what I'm referring to and like still keep the previous context and regenerate the image. And finally, if I switch to a different topic, it kind of needs to drop the previous context and understand that like, hey, this is less, historical context is less important. I'm going to start from scratch, so there is no like Oracle in that cat photo or whatever. So this particular demo is actually open source. You can like go to our GitHub and try it out. It's built with Fire function and it's built with like a few other models, including like SDXL, which are run on our platform. The model itself for function calling is actually open source. It's on Hugging Face. I mean, you can, of course, call it on, at Fireworks for optimal speeds, but you can also run it locally if you want. It uses a bunch of functionality on our platform. For example, like structure generation with JSON model grammar mode, which I think was similar to some of the previous talks from like Outline guys, which we were talking here yesterday. Yeah, so finally try it out. And generally, like how to get started on Fireworks. So if you head out of Fireworks models, you'll find a lot of open source, open weights models, which I mentioned about. They're available in the playground. In terms of product offering, we have this kind of range, which can take you from early prototyping all the way to enterprise scale. So you can start with serverless inference, which is not different from getting to OpenAI playground or something, where you pay per token. It's a constant price. You don't need to worry about like hardware settings or anything. As I mentioned, you can still do fine-tuning. So you can do hosted fine-tuning on our platform. You can bring your own LoRa adapter and still serve it serverless. As you kind of graduate to like maybe like a startup and you graduate to a more production scale, you might want to go to on-demand, where it's more like dedicated hardware with more settings and modifications for your use case. You can bring your own custom model fine-tuned from scratch or do it on our platform. And finally, if you scale up to bigger volume and want to go to enterprise level, where it's kind of discounted long-term contracts, and we also will help you to kind of personalize hardware setup and do some of those tuning for performance, which I talked about earlier. And in terms of use cases, I mean, we're running production for many companies, ranging from small startups to big enterprises. We're serving like, last time I checked, like more than 150 billion tokens per day. So companies like Quora built chatbots like Poe, Sourcedraft and Cursor, which I think Cursor had a talk here yesterday. They use us for like some of the code assistant functionality, and their like latency is really important, as you can imagine. Folks like Upstage and Liner are building like different assistants and agents on top of that. So we are definitely production ready. Go try it out. Finally, we care a lot about developers, you guys. So actually, this is external numbers from like last year, LangChain State of AI stuff, where it turns out we are one of the like after Hugging Face, the most popular platform for where people pull models, which is great. Was very nice to hear. And again, for getting started, just head out to our website. You can go play in the playground right away. So, for example, you can run Llama or Gemma or whatever at the top speeds, and kind of go start building from there. I'm really excited to see what you can build with open models of Fire Function or some stuff which you can fine-tune on your own. And yeah, last point, we are, as I mentioned, OpenAI API compatible, so you can still use your favorite tools, the same clients, or you can use frameworks like LangChain or Llama Index or etc. So yeah, really excited to be here and tell a little bit about open source models and how we at Fireworks focusing on productionizing that and scaling it up. Go try it out, and you can also find us at the booth at the expo. Thank you.
That was a great talk. And now, who here has heard about Devin? Most of the room? Well, so this talk is going to be really interesting for you all. Here we have Scott Wu.
Cool. Okay. Yeah, I'm Scott from Cognition AI, and I'm going to tell you guys a little bit about the early makings of Devin. We're still super early on, and also a little bit about kind of the space as a whole and what's coming next. I thought it'd be nice to start with the demo first. It sounds like some of you guys have already seen some of the videos, but I brought a nice custom one here for the World's Fair today. So I'll just show that quickly. And here I basically said, hey, Devin, this was this morning, by the way, this is a huge scramble. I said, hey, Devin, I want you to build a mobile-friendly website to play the name game. So I have a lot of trouble memorizing names and faces. I don't know about you guys. But I basically just said, here's a TSV file of a bunch of names and faces. These are all the speakers here at the World's Fair this week. And I said, can you set up the game so that you show two different random faces and then show the names of one of them and have me guess which one is which, right? And I give kind of a few instructions on how the game should work. And so Devin is a fully autonomous software engineer. And what that means is Devin has access to all the same tools that a human software engineer would have when it was building, when they're building something like this. And so the first thing that Devin's going to do is Devin's going to make a plan. And you can see here, kind of a basic plan coming out. One of the interesting things about this is the plan changes a lot over time. And so, as you get new information or new feedback, you update your plan accordingly with that too. After that, Devin's basically just running this the same way that a human would. And so if you can take a look, Devin makes a new directory for the name game website, starts a new React app, all the same primitives, works on building it out and building the code, reads the TSV file to take a look at what's going on here. And is just kind of generally working through it and jumping through. It comes out and deploys this first version after some minutes. And I'll just pull this up quickly. So that's what this looks like. It's closed, but not quite there, right? I mean, it's still showing the names, and I think maybe I didn't quite specify that exactly. But you can click the name and got that correct. And so I just went ahead and just gave it some more feedback in plain English. And so I said, hey, can you hide the two names until I click on the answer? And also, can you probably restyle the play again button? It's like, somehow it's a little off on this page. And I kept going and just kind of gave it more and more feedback over time. And I also asked it, hey, can you add a streak counter as well? Can you keep track of how many I got correct and reset to 0? A few of these other things. And the website it ultimately deployed was this one right here. And so this is Justine, for example. Keeps track of my streak, and you can see it's kind of ramping it up. And so, if I were to, for example, if I got this one wrong on purpose, then you would see the streak would reset to 0, and it would go on. And so I actually played this game and learned the names of everyone, which was super helpful, by the way. And you guys can play it too. It's right here if you want to try it out. This has all the speakers. I think it was something like 170 speakers here at the World's Fair this week. So this is kind of a cool example. But I want to highlight how different the world is if software engineering is just this easy. You know, if you can just explain exactly what you want in plain English and get that out. And so, you know, this is obviously kind of a toy use case, and it's perhaps useful, but we use Devin all the time ourselves when we're building Devin, actually. And by the way, obviously, I didn't make this website myself. I just said, hey, can you build me this website with the QR code and whatever, and Devin built that too. But you know, here's a quick example of Devin that we're using ourselves in production. And so, you know, if you take a quick look here, for example, there's this whole search bar, and there's all the sessions, and you can search across sessions, right? Devin actually made that in the Devin repository. You can see here, Bryce is on our team, and Bryce was asking, hey, Devin, can you go into the Devin sessions list, create a search bar component, here's what I need you to do. And so there's a few features about this in particular that are obviously tuned for working in a production code base. You can see here that Devin started from a snapshot. So we have a machine instance loaded where it's cloned from. It has a playbook, so it knows like a lot of the details about our repositories. And then it's also just able to generally work within our Git environment. So you'll see it just make a PR and interact with all those same tools. And so I'll just kind of go through this quickly. So yeah, Devin says absolutely, you know, makes the first pull request. Bryce continues, and again, you're just giving feedback in plain English, right? And you say, hey, this is a great start. You know, now could you add a magnifying glass and make it idiomatic? You know, use phosphor, Lucy. You know, it's up to you, right? And Devin says, yeah, sure, I'll build that. And Bryce says, oh, by the way, no need to test. You know, I trust you. And Devin says, by the way, I'm dealing with a bit of an issue with the login process. You know, it's just like you're working with another engineer, right? And Bryce says, okay, bro. And you know, it kind of builds it all and gets the PR, and this PR was actually merged, and this is, you know, the search bar, right? And similarly, you know, a lot of the API integrations that Devin has were built by Devin. You know, a lot of our own internal dashboards and metrics tracking within Devin were actually also built by Devin. And it's been kind of a fun one to see, like Devin building the company with the company as well. So cool, yeah, I want to talk a little bit about, you know, our journey so far and about what's happening in the space as well. And so, you know, we got started back in November, so it's been about 7 months now. It's kind of funny, we started in a hacker house in Burlingame, and it was basically just, a lot of us had already like lived together at that point. You know, we'd all had our own journeys in AI, and we just knew that we wanted to build something together, and we obviously knew that we wanted to do something in code and build a coding agent. And then that hacker house in the Bay Area, after that there was another hacker house in New York, then there was another hacker house in the Bay Area. So we've been going back and forth between New York and the Bay for basically the last 7 months. I think at this point we are now gonna like settle in the Bay, but it's been going back and forth and getting like a slightly bigger Airbnb each time because the team also gets a little bit bigger. But you know, why Devin in particular? And you know, this is a particular question that I'm really passionate about, which is, you know, language models have been pretty big. I think that's fair to say. And you know, the first wave of generative AI is what I generally call these text completion products, right? And you know, that makes a lot of natural sense if you think about it, that obviously the interface of a language model is text completion, right? You give it a prefix and it completes the suffix from there. And so if you think about ChatGPT, if you think about a lot of these Q&A products, if you think about, you know, writing marketing copy or answering customer support, or even GitHub Copilot and Cursor and products like that, you know, obviously very, you know, a lot of these are really great products. And very natural use case where you have the prefix so far and you're asking the model to complete what's next in the suffix, right? And it does that for you, and that's a tool that's useful, right? And I think we're entering this new wave where, you know, we're going beyond that and actually introducing some amount of autonomous decision making. And obviously, you know, that's typically referred to in our space as agents, right? And you know, there's all sorts of new things that you unlock, right? There's a lot higher bar of consistency that you require, but there's new things that you unlock with that. And so it's been an interesting one because it's both a very deep core capabilities question of getting Devin to solve these, but also a pretty interesting product design problem because I think the UX of agents is something that's extremely new. And then why code in particular? You know, a few different things. Obviously, we're all coding nerds as well. You know, we're all engineers, and so the idea of teaching AI to code is you know, one of the coolest things that we could think of. But beyond that, I think there's a few particular reasons that code with agents works especially well. You know, one is that obviously there's so much more to being a software engineer than typing the code, right? A lot of the work that you're going to do is, you know, you're going to be looking into a bug, you're going to be looking at the different files of the code base. Maybe you're going to be running this or that command. Maybe you're going to be pulling up documentation. Maybe you're going to run the front end yourself to reproduce the bug. You look at this thing, you make this edit, you try it again. All of this work here, obviously, is, that's what software engineering is, right? More so than just typing the code in the file, which leads very naturally to an agentic workflow. Another part which I think is closely related is the ability to iterate with code feedback. And so what I mean by that is, if you were given an entire production code base and you were told, hey, this has this one bug, I need you to fix it, here's the bug. And let's say it's like thousands of files and hundreds of thousands of lines of code. I mean, it'd be pretty tough, honestly, for most humans. It's also going to be quite tough for AIs as well. And obviously, the way that we do this in practice is, you go and add print statements, you pull up the logs, you check the monitoring, you jump back and forth between different files, you try and diagnose it, right? Each of these things that you're doing, you're making a decision and then you're running actual code to find out what happened. And from that, you're able to iterate, and it just gives you a much cleaner path to solve the problem in front of you. And similarly, that kind of lends very well to agents. And the last thing I just want to mention is, how fast model agentic capabilities are improving. And so, 2 years ago, like even something as simple as this name game demo, I think would have been almost unthinkable. And you think about where things are going and where things are going to be 2 years from now. I think there's a lot of, the data, the right training, and so on. That's really, really rapidly improving in the space. And then, again, beyond the capabilities problem, there's actually a really deep UX problem as well. And at a high level, I think what's kind of happening here is when we're building agents, and I think all of us in the space are quite new to agents, the immediate first things I think to map to are, how we use software today, and also how we talk with other humans, right? And so, I mean, even a lot of the features in Devon are essentially looking over your own intern's shoulder. You can see their computer, and you can see what commands they're running and things like that. The thing is, I think an agent is actually pretty different from both. There's a lot of nuances and details of parallel work, information gathering, how it manages context, et cetera, that are super, super different. And it's actually a quite deep problem from a product perspective as well. And just to give you guys a bit of a sense of that, like here's just a kind of a short list of some of the features that we've built into the product. And so, obviously there's Devon being able to use the shell, edit code, browse the web, but there's all these other things, right? Being able to fork and roll back sessions, being able to handle integrations with Slack and GitHub, being able to handle playbooks, to store machine snapshots, to keep track of secrets, to be able to work with the right tools for verification. All of this is part of the actual product iteration, right? Which is, on its own, I think, already an incredibly, incredibly dense problem. And I think, honestly, we're going to see actually a lot more iteration with that over time. And I just wanted to show kind of a new feature which we just recently shipped, which is the ability to use Devon's machine, which is kind of, again, it's the kind of thing that's not always, there's not necessarily a very close parallel in the software that we have today, right? But the ability to just have a VS Code live share in Devon's machine, and if you want to collaborate with Devon and say, hey, oh, there's these couple lines, like, you should make this edit. I went ahead and did that edit for you, and you can just talk with Devon and do that, right? So there's a lot more room to go and a lot to iterate on in the space. One of the other things I wanted to mention too is just how much we've seen it changing our own workflow. So you guys saw like a simple example of Devon building the search bar, but we actually handle tasks in a much more async way now. One of the cool kind of features of Devon, I'd say, is if as an engineer you're working on, let's say, 4 different tasks today, you just give one to Devon number 1, you give the second one to Devon number 2, the third one to Devon number 3. You have 4 Devons that are all running in parallel, and it's kind of turning every engineer into an engineering manager is almost how I describe it. I think the Devons are very like enthusiastic interns is what I'd say. I mean, they try very hard. They're obviously they don't know everything. They get little things wrong. They ask a lot of questions, but you're kind of working with each of them and having them iterate. And so here's just kind of a fun example. I mean, this is literally from earlier today, but we were talking about some particular feature and about what we wanted to build. In this case, it was a pretty simple thing of changing the color, but it's just as simple as just saying in Slack, in the conversation, hey, @Devon, can you just change this thing? And then Devon goes and makes the PR, and then you hit merge, And so, we've had a lot of occasions where we're, in the gym or in the car or something, and now you can actually write code because, you can tell Devon exactly what you want Devon to do. You just don't have your whole computer with you and can't type everything, but being able to just kind of describe what you want to dev in and then being able to review the code afterward actually works really well. So what's next? I think this is a really important question. And obviously, I think the technology is extremely early today. But where do these things go in a few years? And also, what happens with software engineering? I think that there's been a lot of uncertainty about that question. And as we're using Devin more and more, I think one of the big things that we see actually is, this is kind of obvious perhaps, but Devin is not the one that decides what to do or what to build. And there's this core part of software engineering. The way I describe it is like, software engineers everywhere, are doing really two jobs at once, right? And the first job is basically problem solving with code. You're given a problem and you're breaking down exactly what is the solution you're going to build. What is the architecture that you're going to use? What are all the flows and the details and the edge cases that might come up, and kind of architecting your exact solution. And then the second part is once you have that, you're dealing with debugging or implementing different functions or writing unit tests or all of the other things that kind of go into this implementation of something that you want to do, right? And I think right now, the average software engineer is probably spending like 10 or 20% of the time on that first thinking part, and they're spending 80 or 90% of the time on that implementation part. And what we really see is Devin actually just frees you up to do more of the first part, and I think the future of Devin, again, it's very, very early, but I think as Devin gets better, we're going to see more of that where Devin just frees up the implementation for you, where you don't have to go figure out how to set up Kubernetes. You don't have to go like debug all these like APIs that are broken. You don't have to go like deal with version changes or migrations or all of these other things that take up a lot of time in software engineering, right? But you actually are spending all your time on figuring out how to solve the problems in front of you. It's a little more like a mix between a technical architect and a product manager almost, right? And so I think software engineering, the job that we call software engineering, is going to change. But I think practically, like, there's actually going to be way more software engineers than ever. And I think there's a lot of precedent for that too. Programming back then, used to mean punch cards, and then after that, it used to mean assembly, and then after that, it used to mean C, right? And as these things have gone on, I mean, most people aren't using punch cards anymore, but there's actually way more programmers than before, right? And I think one of the things that's easy to underestimate is just how much more code there is to write. And it's funny to think about, I think, because obviously we all love software here in this room. I would say I think software has been the #1 driver of progress in the world in the last 40 or 50 years. And yet despite that, I think our demand for software to be built is actually probably a lot more than 10x what we're currently getting. And so I think what happens is we get to open up the power of software engineering to a lot more people, and every single software engineer gets to be 5 or 10x more effective, but we actually do a lot more software engineering. Cool. Yeah, so that's all I had, but yeah, we'd love to open the floor if there's any questions. Yeah, right here in the front. Great question, great question. So we've been ramping up access. Every week we've been letting on more and more people. We've also been sizing up with our enterprise customers. We have a lot of wait lists to get through, so we're doing it as fast as we can, but we'd love to get you guys access as soon as possible. Yeah, yeah. All the way in the back over there. Yeah, in the red. Yeah, exactly. So in our code base, for example, Devin has all the setup that it needs. It has a machine that's basically instantiated where it can run the dev environment, it can run the server, it can run the front end. And so if you're asking it, hey, I need you to debug this particular thing, it'll just pull it up itself and then reproduce it, and then it'll debug it and try it again. Yeah. Exactly. Yeah, yeah. Yeah, any other questions? Right here? Yeah. Oh, of course, yeah. So, sorry, so someone asked, with all of these simpler tasks getting solved, what happens to, all the junior engineers or the interns who obviously need to learn how to code? I think what happens, honestly, is I think that demand is going to just keep rising with supply. And I think the training process is going to change a little bit, but I think a lot of these core fundamentals of, if you think of someone as, when you say someone's a really great engineer, typically you don't mean that they type really fast, although maybe they do that too, right? You typically mean that they have a really great understanding of problems, they know all the different architectures, they never miss an edge case, stuff like that, right? And so those are the fundamentals that I think are always going to matter. And I think, basically, I think interns or junior engineers are going to get more exposed to getting to use those fundamentals earlier and earlier. Yeah. Yeah. Okay. So someone asked, what are the biggest challenges to realizing the vision of a future suite? There's a lot. I mean, it's basically everything, as you can imagine. I mean, there's speed, there's consistency, there's access, there's integrations, there's the right product UX. And I think all of these things, one of the cool things I think is just how much of a rising tide there is everywhere. And so, obviously we're going to do our best work on it, but every new hardware release is amazing for it. Every new foundation model that comes out is amazing. Every new piece of agentic research. And I think this is the kind of thing where I think there will be a lot of different optimizations that come in different parts of the stack that make this agentic flow better and better and better. Yeah, it won't just be one small thing, but I think it'll be pretty fast.
That's all the time we had. So thank you so much.
Thank you guys so much.